Welcome everyone. In this video, I'm going to talk about the Pauson Khand reaction. The Pauson Khand reaction is a cobalt-mediated 2 plus 2 plus 1 carbonyl cyclization of an alkyne, and a carbon monoxide, leading to a cyclopentenyl moiety. This lecture will be split into two. In part 1, the mechanism, catalytic variation of the Pauson Khand reaction, and the general regioselectivity will be covered. Following this, asymmetric conditions and some closely related Pauson Khand type reactions will be summarized. So let's get started. The Pauson Khand reaction, PKR in short, was first reported by Professor Peter Ludwig Pauson and his postdoctoral associate Ihsan Ullah Khand in the early 1970s, as the name suggests. It was discovered during the attempt of a trimerization reaction between alkynes and norbornadiene. Due to the prevalence and versatility of cyclopentenols, the Pauson Khand reaction was further developed into an applicable level. These are selected total synthesis examples where the Pauson Khand reaction was used to build the highlighted parts of the final natural product. Now, let's talk about the mechanism of the Pauson Khand reaction. The exact mechanism is still ambiguous, but the Magnus mechanism is widely accepted. The starting material is this alkyne dicobalt hexacarbonyl complex, the adduct of alkyne to dicobalt octacarbonyl. According to the Magnus mechanism, the Pauson Khand reaction is composed of four main transformations: ligand substitution, followed by cobalta cycle formation, and carbon monoxide insertion. Final successive reductive elimination liberates the cyclopentenone product. Let's delve into the details of these elementary reactions. The ligand substitution process follows a dissociative mechanism, which means the carbon monoxide ligand falls off first, then the olefin binds at the empty coordination site. The carbon monoxide liberation step should be the rate determining step, since dicobalt pentacarbonyls are highly reactive and carbon monoxide forms very strong bonds with metals. This is supported by the experimental observation that carbon monoxide overpressure leads to a slower reaction rate. The Le Chatelier principle would disfavor liberation of carbon monoxide dissociation. Therefore, facilitating carbon monoxide dissociation would enhance the reactivity and rate, which was successfully achieved by the use of promoters. Various promotion methods have been developed, while amine oxides and sulfoxides were most successful and applicable. These oxides deliberately oxidize as carbon monoxide into carbon dioxide, which cannot bind to cobalt anymore, freeing a coordination site. This leads to a lower reaction temperature and a better yield, as you can see in the chart below. For symmetric alkyne cobalt complexes, the two cobalt atoms are enantiotopic. If a chiral amine oxide is used, one may expect desymmetrization via selective decarbonylation could be possible. This indeed was realized by using brucine and oxide. Related studies will be introduced later in this lecture. Besides the use of amine oxide and sulfoxides, other methods such as photochemistry, silica gel absorption, ultrasound, and single electron transfer activation was also developed. Another interesting observation is that when directing groups such as thioethers and thioacetals are present within the molecule, it can also coordinate to cobalt, leading to a pentacarbonyl complex. These coordinated complexes can induce selectivity by lowering the reactivity of the cobalt complex, as well as providing a rigid environment for diastereomeric or enantioselective reaction. Subsequent olefin coordination is usually very quick, with almost no activation energy. These adducts will usually undergo subsequent transformations very quickly, but the alkene complex has been isolated in the case of highly strained intermolecular cases, such as the one showed in the lower right side. Next step is the cobalta cycle formation step. If the previous ligand exchange step was important in terms of reactivity, this step has its own significance because the regiochemistry, stereochemistry informations are established at this stage. For the cyclization to take place, the two bonds that break, which are the carbon-cobalt bond and the carbon-carbon double bond, must be syn periplanar. This cyclization can be viewed as a 2 plus 2 cycloaddition or a metathesis-like process. As stated earlier, olefin coordination itself is kinetic governed, a reversible process. Before cyclization takes place, two low-energy processes can happen, which is rotation of the olefin and oriental interconversion of olefin between pseudoaxial and pseudoequatorial position. Under normal conditions, the cyclization step is reversible. In order to push the reaction, Lewis-based additives can be used, such as amines, alcohols, or ethers. This effect was first thought as a result of facilitating the initial decarbonylation step. However, further DFT studies have suggested that there is merely any difference in the liability of carbon monoxide, but the transition state of the cyclization step is significantly stabilized by additives. Following the cyclization step, the carbonyl ligand is inserted into the carbon-cobalt bond. For insertion to take place, the cobalt atom must be fully saturated after cyclization. Coordinative saturation may be achieved by a few carbon monoxide ligand or additives. There are two carbon-cobalt bonds, one carbon with sp hybridization while the other has sp3. The selectivity between these two bonds is of no importance because either way will lead to the same product, and the following steps are very fast. Computational studies suggest that sp3 carbon-cobalt bond is favored. Final step is reductive elimination, which liberates the final cyclopentanone product. Besides the desired product, the dicobalt carbonyl complex is also regenerated. This cobalt complex is rather important because a catalytic cycle can be constructed if this complex can regenerate the active adduct with the alkene. Unfortunately, not all Pauson Khand reactions are catalytic. The main reason is that higher cobalt clusters of no reactivity forms after the reaction. This issue has been addressed by using additives, using alternative cobalt sources, or other metals than cobalt. Also, heterogeneous catalysis or use of unconventional solvents showed great potential for a catalytic Pauson Khand reaction, but won't be introduced here. The very first catalytic Pauson Khand reaction was accomplished by using high cobalt carbon monoxide pressure in order to decompose high cobalt clusters to the reactive dicobalt complex state. This condition, however, was very harsh, low-yielding, and irreproducible. First, let's look into the additives approach. The general idea is to modify the dicobalt reagent in terms of sterics so that it doesn't coalesce into high cobalt complexes. But the downside is that it may also lower the reactivity of the reagent. Three major types of additives will be introduced: phosphorus-based, thioureas, and oxygen-based. Triarylphosphines were initially attempted, but they stabilized the reagent too much, shutting down the reactivity. Later, it was found that the phosphines could be used, but the ratio between cobalt and phosphine was very important. Instead, phosphides were quite successful, inspired by a related isomerization process reported by Iwasawa. Professor Chung applied bulky phosphides as the first practical Pauson Khand reaction with good yield. As stated earlier, triphenylphosphine was later found effective, but needs to be controlled very carefully to keep the reactivity. Chen and Yang then reported thioureas as an effective additive. Bulky thioureas were all successful. Tetramethyl thiourea, TMTU, seemed to be the most ideal. However, the ratio between the catalyst and the additive must be controlled carefully. Oxygen-based additives such as water and DME were also successful. Pressurized conditions were required but showed good yields with generally lower catalyst loading than the other additives. The second approach is using an alternative cobalt source than dicobalt octocarbonyl. In this approach, the issue of the cobalt carbonyl reagent is addressed. Dicobalt octocarbonyl is rather unstable, difficult to purify. Use of alternative cobalt source led to significantly better results, not only in terms of reactivity, but also reproducibility. Catalytic conditions could also be standardized using a reliable source of cobalt pre-catalyst. Professor Chung has reported two conditions: using cobalt indonyl COD pre-catalyst and in situ generating cobalt atom by reduction of cobalt ACAC using sodium borohydride. Alkyne dicobalt hexacarbonyl complexes are much more stable than dicobalt octocarbonyl, which they can even be purified using silica gel chromatography. Livinghouse has reported using methylbutyriene 2O complex as a precatalyst, together with silane and amine. Silane reduces the alkyne complex via hydrosylation, generating free cobalt hexacarbonyl. The role of amine is unclear, but consistently showed better results when added. Furthermore, Kraft has developed a pre-catalyst which undergoes intramolecular Pauson Khand reaction itself, liberating the free hexacarbonyl catalyst. The advantage is that silane is not required, and even amines too for some reactive substrates. Besides catalytic conditions, regioselectivity is another major issue of Pauson Khand reaction, especially for intermolecular reactions. Generally, bulky substituents tend to occupy the position alpha to carbonyl, but this is very rough. Directing groups and electronics can also play a role altering selectivity. Generally, this pattern is clearer for the alkyne than the alkene. Electronic effects are more important when the substituents are similar in size, generally positioning electron donating groups at the alpha position to the carbonyl. This polarization effect can be rationalized as a trans effect. However, this isn't always true. For instance, for heterocycle-bounded phenolalkynes, even though thiophenes and furans are much more electron-rich than benzene, phenol groups exclusively takes the alpha position. Now this is it for part 1 of the overview of the Pauson Khand reaction. The other half will be covered in part 2. I really hope you have enjoyed it, and if you did, please leave a like and subscribe for more. Thank you.